Okay, I think that we can start. Um, for the beginning, a few words about myself. My main job is that of a professor at Transilvania University in Brașov, and in this capacity, I conduct didactic activities and also research activities that belong to big data, machine learning, complex networks, complex data protection and privacy mechanisms, among others. And I have also been with Siemens Industry Software from Brașov for the past few years as a researcher. The context of the presentation today is tied to the ever actual fight between problems and solutions. In our case, the problem is represented by different types of malware. And in our presentation today, we'll be discussing about malware that is installed on Android mobile devices. And the quest to discover efficient software solutions to properly detect and block or otherwise process this malware. In this context, it is some specialists and technical practitioners envision an activity that is called adversarial attack. This adversarial attack involves that data, a data packet or an application that has some code injected in it is fetched to the antivirus system. The application looks like a legitimate one to the plain eye and also to most of the antivirus systems. The scope of these adversarial attacks is to offer the opportunity to assess the effectiveness of antivirus systems, to discover holes in those antivirus systems and consequently patch them. Or from the perspective of the hackers, certainly their goal is to find ever more efficient ways to break into those antivirus systems. In order to test our solution, as we will see in the following slides, we have used several well-known data sets to the enthusiasts. Among these data sets, we have Drebin, Sec SVM, Mamadroid, and Opcode SVM, like you see here. What is the principle? As you will see, the presentation will contain in some of its sections pretty technical aspects. So I'll do my best to keep it as simple as possible in order for the message to arrive to you efficiently. So the principle involves that a certain code, a certain piece of code is inserted into a malware. And the scope of this insertion is to look that malware look as a legitimate one. There is also another variant of this technique to insert the malware into the structure of a very legitimate app. And this is what we will be mainly discussing today. As we will see, and this is a glimpse on what we'll discuss later, our system is capable to detect and create proper adversarial attacks with only minimal number of operations, because it uses a randomized machine learning algorithm that is called random search. Initially, and in most of the papers that you will find in the scientific literature, you will see that they mainly use a technique that is called genetic algorithms. A genetic algorithm is mostly a stochastic process which tries to imitate how the genetics work in a biological being. The process that we tested in our lab in order to create adversarial attacks involve two steps. The first step is preparation, and the second step is manipulation of the prepared files. What we manipulate and what we prepare. As at least some of you may know, an Android application is packaged into an APK Android package. This Android package very much resembles to a jar file or to a zip file, and it contains the assets and the necessary code files for the application to run, and also it includes metadata. Metadata is mostly, that is of interest for us, is mostly defined in the Android manifest XML file. It also contains the so-called classes.dex. Dex is an extension that originally was referring to the Dalvik runtime machine of the Android system. Should I briefly explain a little bit on how an Android application runs on a mobile phone? Okay. When an Android developer writes the code for its Android application, it can do so in two ways. The first way, it can write a native code. The native code is written either in Java or in Kotlin. Or it can use some kind of framework, like, for example, Unity, Xamarin, or some other framework that considers other programming languages but still generates Android packages that are perfectly runnable on the Android operating platform. The Android is based on the usage of a Linux kernel, a heavily modified Linux kernel, and each application is allocated its own virtual machine. So each application runs in its own virtualized environment. It's pretty much what Java virtual machine does with the Java application, so that JRE utility or Java runtime environment is very similar to what the Android operating system creates for the Android applications. And initially, the virtual machine that was accomplishing this task was named Dalvik. The actual runtime is called Android runtime. It's sensibly more efficient than Dalvik, either considering the necessary computational resources or the overall responsiveness that it ensures for the applications. So and the classes .dex files are obtained during the build, compile and build process of our Android applications. Okay. There are two approaches in order to create evasion attacks. The first one is the so-called white box evasion attack. As the name suggests, this white box attack allows the attacker or any other interested party to have access to the relevant details about how the attack patterns are configured and their inner workings, while the black box attacks simply prevent any external entity from studying any of the inner workings of the attacks that we speak about. And in order to simulate as efficiently as possible the real world situation, we chose the second option, the black box attacks. Okay. We have been using several utilities. I've already gone through the basics concerning the APKs and the runtime. The other tool is this APK tool that allows us to accomplish a fairly efficient reverse engineering process of our applications. So just as a remark, direct engineering is when you have an idea about an application and you create the architecture of the software solution and then you implement it in a certain programming language. And reverse engineering occurs when we have an already implemented system and we want to extract parts or all of its structure to study it, to understand it, and maybe use it for our future projects. This APK tool is used to decompile and recompile the Android applications. Then, sorry. Then, during the decompilation process, the obtained DEX files that I was talking about are compiled into a human-readable code using a utility, and it's practically a kind of programming language that is called Smali. Smali is freely available on GitHub and can be used by anyone. We have used only freely available tools so that you can replicate the process if you wish to do so. Then we use another tool that is called Suit and also FlowDroid. These are two Java-based frameworks that are used to analyze the Android applications. Among other actions, we have used these two tools in order to construct the call graphs. So the call graphs represent the call patterns for the methods or functions that are part of our software solution. Okay, so I will show you a scheme. Just for you to better understand how the process works. So we have an APK. so an Android package that was obtained following the process that I was already describing. This APK can either be downloaded from the Android application store, or it can be obtained via third parties that offer for download these APKs. Starting from this archive, we disassemble it. We process it using the SMALI that I mentioned, and then we extract the so-called n-gram opcode feature. Not only in this context, in general speaking, an n-gram is a sequence of n characters that is arranged according to the logic of the problem that is under research, and it has a certain purpose. In our case, the n-gram is used in order to combine it with the malware code and make that malware code resemble to a legitimate one, so that we can fool the antivirus software. Then we select the so-called donors. These donors may be regarded as parts of the software applications that can be combined, and so that the resulting mix between malware and n-grams produces code structure that is hard to be detected by antivirus systems. Then the APK is disassembled once again and is processed once again using the SMALI environment, and using the function graph calls that we obtained using FlowDroid and Suit, we can discover the opcodes that are most likely to be called during an application's execution. The opcode, does anyone know what an opcode is? Exactly. It's an operation code, or or some users of the jargon also call it operative code. It's a kind of our application's code that is executed concretely on the device's CPU in order to conduct a certain action that is compatible with the logic of the application in that context. Then, by specifying the opcodes, we establish the points, the sections in our application's programming code where it is most likely that we can insert the malware snippets, so that it blends well with the application structure, but is also easily to be executed in order to attain its purpose. Then we use the information that was gathered, and we obtain eventually the malware application. And this malware sample is then transposed into using a kind of injection, and a new Android package is created that is being fetched over to the target antivirus system or malware detection system. A side note, as I have already mentioned, the Android environment uses a kernel that is based on the Linux kernel, and considering this respects all the principles and the security models that are valid for a Linux kernel. I mean, which of you have some experience with Linux and file? So how do we define directory and file access? What mechanism do we use? Yes, and in order to set the read, write, or execute rights. Yes, you are there, but you haven't said it all. So there are three types of users that an Android file or directory has. We speak about the user or the owner of the file, then about the group which this user is part of, then the rest of the world. In the jargon of the Linux users, you may find this as UGO or UGO. And each of these users have three have a number in the numeration base 8. So considering that is the numeration base 8, we can only use figures up to 7. When someone when a file or directory offers access, free access, complete access to everyone, it will have assigned a 777 number, and by customizing the values of these numbers, we can set fine-grained permissions. So Android follows the same principles. So even if an antivirus is installed on the phone, it may not get immediate access to the contents of the root partition of the phone, especially considering that the phones that are sold nowadays are not rooted. So the phones that are commercially available forbid access of the end users to their root resources, including the root file system. This means that an operation that is called routing, or some of you may have heard about it in the context of Apple phones, there is called or was called jailbreaking, has to be performed in order for us to get access to all our devices' resources. But still, by injecting malware code into the application, we can create APKs that bypass the security of our Linux-based Android system and produce harm at least in the virtual environment that is assigned to our application. Okay. As I've said, our adversarial attack system involves the usage of the random search algorithm. This random search is used here as a black box optimization method. What this means? A little bit of formalized context for each malware sample that we denote with Z. The proposed model utilizes random search to determine an optimal subset of transformations that we designate as delta in order to generate an adversarial example. And here we were faced with two options. Most of the scientific literature that we have studied consider genetic algorithms. In the case of genetic algorithms, the determination of an adversarial example requires anywhere between 25 and 30 transformations. The transformations simply confirm to the logical flow that is presented in this diagram. And you can imagine that one transformation that should go through all these steps requires quite a lot of computational time. So the reduction, optimization of this number appeared to us as a mandatory step. Therefore, we didn't go the way that it is suggested in the scientific literature that we reviewed during the initial phase of our research, and we have tested and subsequently adopted this random search heuristic. This random search is very advantageous because it does not need information about the current result that the current iteration generates, and it does not need to know what the previous result in the chain of iterations was. So it can be perceived as a kind of autonomous entity that acts in the context of, in the logical context of our proposed algorithmic model, and which consequently uses minimal computational resources that, but the provided results are at least equally as accurate as they are using genetic algorithms. And of course, a few orders of magnitude faster. So this is a description of the logical flow of our application. I have did my best to explain it and comment it as much as possible. So as input, we have the original malware sample that will be customized through the logical flow that I was describing, and delta is the action set, manipulation, preparation, and other auxiliary actions that are being performed. Then the objective function and all the other entities that are of interest for us. And I've described the structure of one iteration. Even studying this pseudocode, you can easily understand that logically and computationally, one iteration is fairly complex. This is why it is absolutely necessary. It was necessary for us to optimize the process as much as possible. And finally, we provide as output the adversarial example and the transformations that were used to create that adversarial example. Of course, of maximal interest, it's this adversarial example. Once again, by adversarial example, we understand the modified piece of software, in our case, an Android package that is customized using that flow that I described. And we had certain research question. Please. The objective function is a function that we use in order to test the effectiveness of our model against it. So it's not strictly specific to our discussion today. It's a concept that is well known in machine learning and artificial intelligence. So we have a model, and that model conforms to a certain mathematical and logical structure, and we define an objective function that we can use to fine tweak our model. It is not a universal recipe for in order to describe this tweaking. In some cases, tweaking may mean to maximize the value that is output by that function. Or in some cases, we should make it minimal. So, in short, it may be modeled through a mathematical function that is used to calibrate and test the accuracy of our model. Exactly. We actually we have used several loss functions. For example, when we have selected those n-grams, the sequences of strings that get embedded in order to obfuscate the malware. We have used distances in order to determine the structural validity of those n-grams. Yes. So we have used what you said, among others. It's when you create an objective function, is absolutely necessary to understand the logical structure of the problem. And by understanding it, you can go and start modeling. And a proper modeling simply implies that you get the result that you look for in terms of, in our case, in terms of accuracy. And here, accuracy means that the antivirus is fooled into believing that an infected adversarial example is a benign piece of software. And this is the list of research questions that we had as a reference in order to validate the outcomes of our research. And as experimental, as main experimental setup, we used an Alma Linux workstation that was installed on an AMD Ryzen 5950X system with 128 gigabytes of RAM. As I've said, we have used several reference data sets and target detectors. Each of the approaches is described into a certain paper. You can easily find all of these papers by using, for example, Google Scholar. So scholar.google.ro or .com, as you wish, and you will find the respective papers so that you can find the reference approaches. And all of these models have been used and experimentally tested in several papers. Among them, one of the most relevant ones is Pierazzi, which was published in 2020, and also Zhang and his team, a paper published in 2021. In order to evaluate the effectiveness of our proposed model, we have gathered the data set, and we have also used the services of the VirusTotal platform. Are you familiar with the VirusTotal? Yeah. So it's a platform that gathers behavioral data from as they want from all the antiviruses that are commercially or freely available on the market. And also we have used in order to create the representation of legitimate benign Android applications, we have used the APKs that are provided by AndroZoo. These are both freely available to anyone. So if any of you would like to replicate the experiments that we conducted, this can be done fairly easily because every resource is available, every data resource. The data set that we managed to gather contains both accessible and inaccessible data items. So the inaccessible data items are simply not provided by the authors, or we attempted to download the data set and we discovered that they are corrupted. So several concrete factors made us to classify part of the data set as inaccessible. So we used for the training process, we use 90,000 benign samples and 20,000 malware samples. Then, in order to tweak the proposed model, we have been using 20,000 benign samples and 20,000 of malware samples. For those of you that are familiar with how a machine learning model is designed and tweaked and trained, this can be somehow assimilated to the training, validation, and testing stages for those models. The only difference is the proportion between training and validation. We know that there is a recipe, 70%, 30%, or 65, 35%. It depends. Here, the proportions are not exactly the same. A few remarks. There is no overlap between the inaccessible and accessible datasets. So semantically, we did our best to ensure that we lose no important semantics while classifying those as inaccessible. And another problem that we tried to our best to overcome was the so-called temporal bias problem. So we attempted to collect as uniformly as possible samples, software samples for our experiments in the period that is defined in this graph. Of course, applying this strategy, you could consider any other time period. And you can see here that the distribution of the collected malware samples and software samples is pretty uniform. Okay. We have used several metrics in order to test the effectiveness of our model. We have first the two pair. We'll find it in any machine learning based system or approach that tries to assess quantitatively its accuracy. It's true positive rate and false positive rate. So true positive rate measures the number, the amount of samples that were detected as positive, and they were actually positive. And the false positive rate designates the amount of samples that were classified as positive, but they were not actually so. And then we have used two metrics that are customized and specific to our use case. It's the evasion rate. So we tried to measure how many of our adversarial examples are capable to trick the malware detector into believing that they are actually harmless. Then is the evasion time. The evasion time is nothing more than the time that is required for an adversarial example to be fully constructed. And first, some graphs that we generated. You can see here that the greater the size of the payload is, the higher the value of the ER metric is. This is to be expected as the evasion rate is greater as long as the adversarial example is constructed in a more precise way. Then the greater the number of queries is, then we obtain the same effect. We increase the values and the effectiveness of the adversarial examples. And in this table we tried to, please. Query is thinking about the diagram that that you saw. A query is one step, one iteration that is necessary in order to go through that diagram. Yeah. So it's a generic term for the initiation of such an iteration. And here we've offered the values of these metrics, and apart from the basic metrics that I mentioned, we also have a number of transformation and adversarial payload size. The transformation imply that the original legitimate application goes through a series of transformations that suppose injection of malware code into their structure. And speaking about of software labels and hardware labels, these are confidence scores and level of the accuracies which our application consider. I remind you that the level of accuracy here imply that the malware-based sample is classified as benign. Okay, so um, what can be said? It can be said that apart from the genetic-based approaches, it is an increase in the accuracy of the created adversarial examples. Then, it is a significant decrease concerning the number of iterations that are required in order to generate an adversarial example. Then, considering just two of the data sets that were considered for our experiments, we have determined experimentally a reduction of the time on average by 41% and 37% of the whole process, which is again significant apart as compared to the approaches that were reported in the papers that we mentioned in the presentation, in the previous slides. And another very important remark, most of the approaches that are reported in those papers are white box attacks. So the attacker has complete knowledge on the structure of the application and on the structure of the malware that will be injected into the benign application. And using our technique, we use the black box, so no knowledge about the structure of the application, and we obtain similar levels or in some instances even better than the white box based approaches. Okay, so we have also conducted an experimental attacks against 4 baseline attacks that are described in these 4 papers. A baseline, when you hear talking about a baseline, you can think about it as a reference to which you can relate in order to compare your own constructed model. And the results were the ones that I've mentioned. Okay. Experimentally, we have determined that our model is capable to evade most of the most significant approaches. These are Drebin, SEC, SVM, and ADEMA. You can find the full description of all these models in the literature, both in the literature, and each of them has a dedicated website. And the authors fully describe their structure, their purpose, and how you can use them. And we again managed to generate evasion rates of more than 90% with a maximum of 7 transformations, as opposed to the 28 that was the case for the genetic algorithms based solution. Okay, so essentially our black box based attack is comparable and sometimes better to the white box solutions. And we have also selected 3 instances that are reported on VirusTotal. we have selected the instances that were considered as the most active at a given moment. I'm not really sure about why total AV appears there, because according to our experience is not among the top 3 or 4 solutions, but at that moment VirusTotal reported it as part of top 3. So we have selected total AV, AVG and Avast in order to conduct our tests, and the result was that the created adversarial examples using that scheme that I presented is able to trick all 3 antiviruses with only a few queries, which is a result not to be sniffed at. Of course, speaking about the research question 4, our model can effectively deceive the solutions that I mentioned with an average of 73.95%, which is a failure rate for an antivirus that is high, is very high for any respectable antiviruses. It's not to say that those 3 are not respectable, but it's a new kind of malware sample which they are not fully prepared to recognize and process. Okay, we have ensured that our model is applicable to as many as possible of the adversarial models and antiviruses that are used, and it seems to be the case. And of course, I have mentioned this achievement. Mainly, research question 6 relates to the comparison between the genetic algorithm-based and the random search based approach. So it is an enhancement of on average 36.5% concerning the evasion rates, and an acceleration of the execution times by 3 times on average. Of course, one of the most one of the problems that decreased the evasion rate, you saw that I mentioned around 74% for the VirusTotal instances. This could have been even higher, but the injected n-gram, so adversarial n-gram into the benign application, was in some instances excessively high. And being excessively high, the antivirus figured out that that n-gram is unusually long for a mobile application, and it flagged at suspect that adversarial example, or APK. So this is one of the aspects that should be improved in several in future versions of our approach. And of course, the random search algorithmic model may also be improved and replaced with even more efficient solutions that would further reduce the number of queries that are necessary. So, in essence, this is the main presentation of our approach. You can get in touch with me anytime that you want. if you are interested about this specific problematic, and I will help you as much as I will be able to. So this is my email address. Thank you very much for your attention, and feel free to ask questions as you like. Please.
Do you have any resources we can look at to study more about this subject? To study this subject in more detail about the malware analysis using AI?
Oh yes, the scientific literature is fairly rich in this respect, and you can simply conduct a simple search on Google Scholar. So Google Scholar is my favorite scientific resources search engine. So you go there and simply use AI, malware, and you will find a lot of papers that approach this subject. And apart from this, in order to be able to fully test the your experiments, so if you read something, you read a paper and you figure out that that is of interest to you, you may want to implement something, an application or a system that is compatible with that model. And of course you should use a database. And some of the databases that are very useful I mentioned in the presentation.
Yeah.
Of course, they are not all. It's impossible to provide an exhaustive enumeration of all the resources, but to start with, just look on Google Scholar for a few articles. I would advise you to use a filter starting from 2020 or 2021, not earlier.
Yeah.
And there are also some less scientific but technical trainings that you can find on the matter. But first and foremost, the scientific papers.
Yeah. Thank you.
You're welcome.
Thank you. So what is the actual performance impact on the applications that are being injected with this code? Do you
Negligible.
notice?
So the most of the computational time is spent when creating the adversarial example. As soon as the application exists and runs as an adversarial example, the performance penalty is absolutely negligible. I would say that according to our experiments, it may increase the running time as compared to a fully clean application by, on average, 4 or 5%.
Okay. But compared to the already injected application, it does not. So we have the injected application and we have the injected application with this evasion technique. And the difference in performance between these two is negligible.
Negligible.
Okay.
Yes.
I understand. Thank you.
So most of the time is spent to create the sample. Yeah.
So I was wondering when training your artificial, is it on?
I think so, yeah.
Yeah. So when training your artificial intelligence, I was wondering on were you training it on Windows or on Linux? And I have follow-up questions based on the
I
answer.
trained it on on an Alma Linux system. So Alma Linux, for those of you that are familiar with Red Hat or CentOS, Alma Linux is a newer distribution that is fully compatible with CentOS and Red Hat. So on Alma
Yeah.
Linux, yes.
Yes, and when training the AI, were you relying on CPU or on GPU? Because from what I have had experience with is that Linux has major issues seeing the graphics card. And did you have similar problems? And if so, what techniques did you use to overcome them?
Yes, it's a good point. We had to use a customized version of an NVIDIA driver. So our GPU was an RTX 3090, and there were some performance problems when using the standard driver, because there is a driver that is provided for 3090 on Red Hat, and we had to use the help of the community to slightly customize the driver, and we were able to use the GPU. So we conducted a comparative analysis between CPU-based and GPU-based, and we have found that GPU does not bring fundamental advantages in this case. So we finally stuck with CPU-based processing.
Okay, thank you.
Thank you very much, and we'll keep in touch as you wish.